So here we left off here on page 195 in your notebooks. So where we left off, we assumed that we'd already done this. We'd already checked the errors. Like, let's just go back to the previous page, and we did these confidence intervals. Remember what we're doing here. We're doing a transformation of variables. We did a log of both the x's and the y's, and then we saw that we had to get confidence intervals on our original variable after, we get confidence intervals on our logged variable the usual way. We just use this, 68% of the time we're within 2 standard deviations of the errors, and then 95% of the time, 68% of the time we're between 1 and -1, within 1 standard deviation of the errors, and then 95% of the time, assuming, this is an approximation, assuming basically normal distributions around of the errors, we are within 2 and -2. And that's how we built these confidence intervals. But remember, they were for the log prediction, for the log of the brain weight. And then we had to do this 2-step process. For the log, we did the usual confidence intervals. That was for the log of the brain weight. But then to get the brain weight itself, we had to exponentiate these endpoints. And we no longer had these symmetrical confidence intervals. That's what we did, but we assumed the error assumptions were met. Well, they really weren't met. They were sort of met, but now we're going to really look at them and see if we can do a better job of fitting this. Here, let me just show you. If you recall, we said, okay, after taking the logs, it was a whole lot better than it was here. Here it was a mess. Then we took the log of both the body and the brain weight, and we saw it looks pretty good. The fit isn't great, but it's a good start. This was back on page 192, and we got this, fairly good fit. Remember, before we didn't even have a correlation. Our correlation coefficient was about 0, right? But now we realize, let's see if we can clean this up a little bit, okay? So now we're going to do what we said we were going to do before and make a scatter plot of the residuals. First of all, okay, so what we want to do, here's our actual graph here, our scatter plot of log body weight versus log brain weight. And we can see that the residuals do form a pattern. It's not great. We have this group right here that seems to have a steeper slope, and we only get a good fit in the middle. Here we have strong positive errors, and here we have strong negative errors. And then we have this other group here that seems to have a flatter slope. So it looks like we have 2 groups, and you can see it. This is our actual plot, and sometimes the residuals are here, but sometimes they show up better when we actually do a residual plot, which is instead of straightening this out, this is just the errors around this residual plot, just plots the residuals, the errors around our predictions on the y against the x's here. So you can see it much more clearly, right? So the arrows don't look like they're independent. That's the problem. They certainly form a pattern. And again, we have these 2 groups here. So who are these groups? What accounts for this? Let's look at the data and we'll be able to see. Okay? So let's look at this on our... So remember what we're doing here. So let's just get to the scatter plot. And we're on the x-axis is body weight, and then brain weight, and there's that terrible regression, right? Even a slight negative correlation, so we logged both sides, and we saw it was much better, and it looks like this. But then we have these 2 groups here. And so, who are these? So let's see, that's Brachiosaurus, Diplodocus, Stegosaurus, Tyrannosaurus rex. These are all dinosaurs here. And these are the mammals. But it only does a good fit, we saw last time, for the cat. And this is the kangaroo. For the animals in the middle. For the animals way down here, like the mouse and the golden hamster, it's not a good fit. It over-predicts. Look at that. They have very big negative errors here. And up here, for the ones who have, it predicts the brain. It really underestimates the brain for the African and the Asian elephant, and for this animal, human, and the chimpanzee. So these animals, so we can do a better job of fitting them by doing what? By splitting it into two pieces. So dinosaurs and humans, not humans, mammals. These are all land animals. All right, so let's do that and see if it fits better. So we'll choose a split here, and we'll split on dinosaur. So these are the 24 animals that are mammals, and these are the 8 that are dinosaurs. So let's do that. We'll choose a split here, split the plots. And now you can see, if you turn your page, this is the diagram that that we have on the next page. And do you think it improves the fit? Yes, the fit is, look at the overall regression. Well, it certainly improved the fit for the mammals. Certainly did. And R went up, the errors went down, and it improved the fit for these somewhat too. Now let's see if we combine the plots, what does it look like? All right, so as we said, we did a much better fit for these. Now, it looks like we should include an interaction term, right? Because the slopes are different. But interaction terms are kind of complicated. Let's just see. These dinosaurs are all sort of in a clump. This isn't fitting them very well. What if we force them to have the same slopes? Let's try that. Show equal slopes. And let's see how much it's improved here. So we'll show equal slopes. And see, it doesn't really change things much at all. And we have a much simpler model. Because these dinosaurs were all sort of in a clump here, so it doesn't really, whether we show it, see how it doesn't really change things much? And it makes a much nicer model. Basically, we can't do a great fit for them because they're not spread out enough. So this does as good a job almost as the other one. So let's just keep with this. And that, and then we'll do a multiple regression model. So let's just see remember how to do that. So we'll go back here, and here we'll choose the y variable as what? Brain weight, but we want the log of the brain weight. And then we'll have the x variables, we're going to have 2 of them. One will be the body weight, and we're going to transform that to be the log of the body weight. And then we're just going to add dinosaur as well. And we'll do this. You can see now we have a multiple regression equation. And if we look at the errors now, let's look at the errors, and we'll see they should be cleaned up. Let's show the error plots. Okay, and it shows, look how much better the errors are here. And here's a histogram of the errors that looks a lot more normal. So this looks like a nice model. So now we have a multiple regression model, and we're going to do some interpretation of that model. Okay, so let's go back to that's what we did in the notebook, and let's go back to that. All right, so here's what we did when we split them. Have we succeeded in improving the fit? Yes, very much so. And now, let's see, we've got these two regression equations here, and the errors are nicely cleaned up. Yes. And you can see the histogram of the errors on the next page. Also, remember, we want them to be roughly normal. We're not going to get them exactly normal, but also see histogram of errors on next page, so you can look at that. That's where I put them, right here. Looks pretty good. Not perfectly normal, but it looks nice. And now, here's the output of the multiple regression equation. So let's write this equation down here. This is these are our slopes right here. So it's the log of the brain weight is equal to what? This is what we're looking at right here. Okay? This is our best fit right here. So the intercept is 2.257 plus 0.7263 times what? Times the log of the body weight, and then minus 4.833 times this variable dinosaur. And how did we code this variable? Well, this variable is coded as, here, I'll write it here. This is coded as, if you're a dinosaur, it's 1 if dino and 0 if mammal. It's a 1-0 variable, okay? So now, I just want you to note two things, that this right here, including dinosaur, breaking into two groups, improved our R a lot. This went up compared to the, it went up from, what was it before? 0.6468. So that's nice. And this went down. This went down. So this went down from, well, this was SD errors, but it would be slightly bigger if it was SD plus, but it went down quite a bit. It improved it. So these went down. So we have a better model. We clearly have a better model. We could see that. Now it says, write the multiple regression equation and show how it's the same as the two simple regression equations. So I want to show you how it's the same as these two simple ones. Why don't we do that as an iClicker? So let's just let's just get out your iClickers, and we'll, what you want to do is we want to write it for mammals, what the log of the brain weight is, and also for dinosaurs, okay? So let's just go to the screen and do that. Okay. So just choose one of these. For mammals, this simplifies. This is not hard. Just a few more minutes, a few more seconds, really. A, B, or C. I'll write it down here. All right, so let's stop it. And What did you choose? The answer is A. Good, excellent. All right, so now let's look at because you're just plugging in a 0. When it's mammals, it's 0, so you've eliminated that. All right, now just next one. All right, so for dinos, what does it simplify to? All right, so I'm just going to stop it now. Everybody have a chance to vote? Okay. And let's see what you said. And it's the last one, C. Great, perfect. Okay, so now let's just go back to the document camera and write that down. So now you just plugged in a 0 or a 1 there, and we can simplify this one right here. This is what you chose. Sorry, what happened here? I'm really sorry. What happened? It's annoying. All right. I'll go back to the PC and now go back to the document camera. Maybe it'll work this time. Okay. It doesn't look right. Try that. All right, so now we're back. And so we just want to simplify this, add these two together. So if we add those two together, combine those two, we get negative 2.577 plus 0.7263 times the log of the body weight, which is exactly the same as these two equations here. So that's the idea. And now, why don't we interpret this equation here? Let's look at this equation and just understand what happens to these coefficients when you change back to the original variables. So let's look at that. And we're going to be doing, this is a sort of practice for our next section is logistic regression, where we're going to be doing a lot of interpretation of coefficients. So it's good to do it here where it's simpler. All right, so what is the multiple? Okay, so here we've got this. I'm just copying it down from what we had on the previous page. This is what we got. That was our intercept plus 0.7263 times the log of the brain weight. And these are all natural. The body weight, times the log of the body weight. And then minus this factor for dinosaurs, because they have smaller brains. So when we exponentiate, what we get e to the 2.257. This is addition, so that's going to be multiplication, times e, and I'll rewrite it, log of body weight, times 0.7263. This is multiplication's commutative. I just wrote it this way because this all simplifies to body weight, times e to the negative 4.833 times dino, which is either 1 or 0. All right, so this right here is the same thing as e to the 2.257 times the body weight to the 0.7263 times e to the negative 4.833 times dino. So I just want to show you that these coefficients, just to make you aware that these coefficients here, this, and this, become these exponents here once you go back to the original variables. Well, here it is again. This is the same thing we just did. So here was our original, and here's our slopes for them all, and then they become exponents once you anti-log. So remember, dinosaurs is a binary variable coded 0 for mammals and 1 for dinosaurs. So this equation simplifies, we just did it, simplifies to what? For the brain weight, we did it in the log, but for the brain weight, right here, it simplifies to what? E to the 2.257 times the body weight raised to the 0.7263 times, we'll put a 0 in for dinosaurs. So we have e to the 0, which is just times 1. Right? That's all we have, times 1. And what does it do for dinosaurs? What do we have? We have the same thing. So the e to the 2.257 times the same body weight raised to the 0.7263. But now this dinosaur is what? When it's a dinosaur, that's 1. So we have this factor of e to the minus 4.833 instead of times 0, which we have times 1. And so that, if you, it's approximately equal to 0.008, and it's approximately equal to 1 over 125. So basically what we're saying is what? That for the same, relative to their body weights, dinosaurs' brains are smaller than mammals by a factor of 1 over 125, by a factor of e to the negative 4, to the negative slope for dinosaurs, to the slope for dinosaurs. Okay? So the brain weight of dinosaurs, this is the factor, this e to the slope for dinosaurs, e to the negative 4.833, which is approximately equal to 1 over 125. How do you interpret the coefficient for dinosaurs? How do you interpret this? When you just look at that, how do you interpret that? It's negative. Why? You just would say you'd think it's negative because dinosaurs are coded as 1, and so it means it's negative because dinos are coded as 1. If they were coded as 0s, that would be positive, and we'd say mammals have a bigger brain relative to their body. It's negative because dinosaurs are coded as 1 and they have smaller brains relative to their body size compared to mammals. So that's the idea. So this factor, so it's just, I just want you to get a feel for how, when you anti-log, what happens. So this factor right up here, this coefficient becomes where does that factor appear? Where does that, it appears right there. We just circled it. Okay? It's the slope it's e to the slope. So the regression equation, so why don't we just use this this regression equation now, and this one right here, and to predict a 90 kilogram mammal, okay? So for a mammal, what do you get? So for a mammal, we'll just put 90 kilograms in for the body weight. That's all. And then 0 here. So it's this right here. So for the mammal, we just get the brain weight. This is really just arithmetic. The brain weight equals what? E to the 2.257 times 90, that's what we're putting in, raised to the 0.7263. And I did that and got 250.94 grams. It looks like you're getting a bigger number, 90. No, they don't have a bigger brain than they do bodies. This is in kilograms and this is in grams. That's why it looks like that. Now, what do I do for a dinosaur of the same weight? For a dinosaur of the same weight, everything's going to be the same. The brain weight, not the log, the brain weight is going to be the same. So we'll just take 250.94, but now we're going to multiply it by that e to the negative 4.833, which is about the same as dividing by 125, and you get very close to 2. Okay, so let's just do, this is really easy, but let's just do this one as an iClicker too, just to keep, make sure you understand. So we'll go do problem this F. So we'll just go to the next question and start this. Okay, so let's stop this, and the answer should be A. Good. All right, so let's go back to the document camera and just write that in. That's all we're doing here. We're saying, okay, you just multiply by that factor, which is about 1 over 125. Now let's move on to the next page. And we're going to look at another violation of our assumptions when you have these violation of the homoscedasticity, the equal spread along the regression line. Sometimes we said we have this fan-shaped errors like this, and a common way to correct for that is by taking the square root of the variables. So let's look at this. This is from our own data. We often ask you this question: how much do you party and how much do you drink? And we get, this is from actual data, and we got fan-shaped. So you see how the errors increase as x increases. So that violates that assumption of equal variability across the x's. And you can see it here's in the residual plot. It looks the same way, like that. And so the linearity looks pretty good, but errors increase as x increases. And why is this a problem? It's basically a problem because we're using the same standard deviation of these errors across the plot, and they don't apply equally. Here we need a much bigger, and here we need a much smaller. So we don't have different, we don't calculate, we calculate one, it's a standard deviation of the errors. You just have one number, and you can't, we can't apply it across the whole plot. We just have one, but it's not the same, okay? So we're using the same across all x's, but it's not the same, as you can see. So the most common way to correct for this is by taking the square roots of both variables. So let's try that. So we did that. And this is, you have a homework problem on this example, but it's taking it once, it's turning into a multiple regression example, adding gender, but you're going to be doing essentially the same thing. All right, so we took square roots of both sides, and now it looks better. So now we get this regression equation. You can see that R went up here. This is improved. And so we get a better fit. Did R change? Yes, it went up. What was it on the previous? There. It went up from 0.7718 to that. So it increased. All right, and here's our regression equation right here. So what are we saying? We're saying the predicted drinks, the predicted square root of the drinks, we're predicting square roots of drinks, I'll put a little hat over it to say predicted, is equal to negative 0.1893 plus 1.083 times the square root of the party hours. All right, so now if we want to make a prediction for drinks, we have to first make this, prediction for square root and then square it. So let's do that. So to go to drinks, we'll have to first get the square root of the drinks. The square root of the drinks is equal to what? Negative 0.1893 plus 1.083 times the square root of 25. And so then I got that is 5.2 approximately. Square root of drinks. But that's not a natural unit for drinks, so we want to square it. So when we square it, we get the drinks. So our best estimate for drinks for somebody who parties 25 hours is 5.2 squared, which is about approximately 27. So that's drinks, and that's square root of drinks. So that looks about right. I mean, what was our original equation? Our original equation said that for each extra party hour, people drink about one more drink, a little bit more than one drink, and that looks about right. But we were able to put error bars around it now, whereas before we couldn't. So we get about the same estimate, but we're able, because we had a good linearity here. It wasn't like we have a nice line. That wasn't the problem. It's just we couldn't apply our error bars. So now how are we going to apply our error bars? Well, we'll have to do it in two steps, like we always do, right? Why? Because these, we're going to add, this is going to be our margin of error. So we're going to add, for 68% confidence interval, we're going to add one of those for, because we can now assume normality. We now can use this, but it's for the square root. We can't apply this to the drinks. So we have to do it in that two-step process again. So the step one, to apply it to this, we can't just say 27 plus or minus that. Okay? We can't, because this standard deviation of the errors is in square roots. It applies to the square root of the drink. So we have to do it in two steps. So step one, so our 95% confidence interval for the square root of the drinks is equal to our estimate for the square root of the drinks, right? Plus or minus the 95%, I'll just write it here. The 95% confidence interval is going to be equal to our estimate plus or minus, 2, because that goes with the 95%, times the standard deviation of the errors. That's what we're doing here. But this only applies to the square root. So our estimate was 5.2. We're using that one. And then we can say plus or minus 2 times 1.06. All right? And when we do that, we get, when we subtract the 2.12, we'll get what? 3.08. And when we add 2.12, we'll get 7.32. So those are our endpoints. Those are our endpoints. Sorry. There we go. Agreed? Now, what do we do for the next step? Step 2. Let's do this one as an eye clicker. See if you remember what to do there. Okay, so let's go over to the eye clickers. Okay, so this is what we want. All right, so let's stop it. This is kind of a hard question, but think about it, okay? All right, so now let's see. So the answer is C. Okay, I understand why you had a little bit of difficulty with that. Let's just go to the next one and see if it helps. All right, so try this. This is not the same as this. A squared plus B squared. See if you can figure this out now. Okay, let's stop it and see if you get this. Great. Yes, it is B. So let's look at Y. So let's go back to the document camera here. And so we have to do this in 2 steps, right? Once we first, you have to get the endpoints and then square them. That's not the same thing as saying 5.2 squared plus 3 or minus 2.12 squared. It's not the same thing. Here, why? You can't, let's just write this down here. So this is equal to what, first of all? This is equal to 9.49 to 53.58. And 27 is not the midpoint of this. You can't express this as 27 plus or minus something. So you can't write the confidence interval as what? We can't write it this way. Once it's in the, you can't write it as our estimate, which would be 27, plus or minus anything. Because, and this is the key, because once you transform the variable and figure out the error for the transform variable, then when you translate it back, so once translated back, we don't have symmetrical confidence intervals anymore. Once translated back to the original variables, our confidence intervals are no longer symmetrical. The estimate is not in the middle. 27 is not the midpoint of those two. Our estimate is not the midpoint of that. Whereas 5.2 is the midpoint here. Our confidence intervals are no longer symmetrical. And why? Just because of the arithmetic. Are no longer, can you see that? Symmetrical, that's what that says. Why? Because basically, if they'd have to be, because A plus B squared, our estimate plus our error squared, is not equal to A squared plus B squared. It's equal to A squared plus B squared plus 2AB. So you can't just do it that way. You can't just say, oh, 5.2 squared plus or minus this squared. Okay? And you can't do it with logarithms either. So you get these asymmetrical confidence intervals. Always. They're always symmetrical around your transformed variables, but when you put it back into the original variables, they're no longer symmetrical. So that's the idea.